Hi everyone, and welcome to the second part of the first lecture, in which we are going to introduce number sequences. So, what are number sequences? Whereas you can expect, they are sequences of numbers, typically integers, in this course. And so, here we can find examples of four different number sequences. And so, the question that we can now ask ourselves is, what number is next in each of these sequences? Um, and also, then we can think about how we would describe each of these sequences in English. So let's look at the first sequence. So the numbers are 5, 7, 9, 11, 13. And the next number in this sequence that comes here is 15. And how will we describe this sequence in English? There are a couple of different ways that we could describe it. One is, for example, that we get the next number in the sequence by adding 2 to the previous number. Another way that we could potentially describe this sequence is that these are odd numbers starting with 5. And so, as we will see, there are often several different ways to describe how numbers in a sequence are generated. Not always, but that's often the case. Let's look at the third sequence here. 1, 4, 9, 16, 25. And the next number in the sequence would be 36. So how do we generate this sequence? Well, the first number in the sequence is 1. That's 1 squared. The second number is 4. That's 2 squared. The third number is 9. That's 3 squared. 16, 4 squared. 25, 5 squared. 36, 6 squared. So the way we generate it is by squaring the position number of the entry in the sequence. So you can already notice that we use two different ways of describing the sequences. So one is by relating the number in the sequence to its position, which is what we did just now. And the other one, which we did in the first sequence, is by relating the number in the sequence to its predecessor. And you can think about the other two sequences on your own and come up with solutions. So these two ways can actually be formalized as two different ways to formally describe a sequence. So the one where we relate each term by arithmetic operations to previous terms, it's called the recursive formula. And in this case, we also need to initialize the initial terms in the sequence. And here is an example. So this sequence can be described as a of n is equal to a of n minus 1 plus 8. And to be able to generate the sequence, we also have to initialize a of 1 to 1. So if we apply this formula, we get that a of 1 is 1, a of 2 is a of 1 plus 8, which is 9, a of 3 is a of 2, which is 9 plus 8, which is 17, and so on. Another way to describe this sequence is using so-called closed formula, where each term is specified by arithmetic operations of its position in sequence. So in this case, this is the formula that describes the sequence, where a of n is equal to 8 times n minus 7. So a of 1 is equal to 8 times 1 minus 7, which is 1. A of 2 is 8 times 2, 16 minus 7 is 9, and so on. So most sequences can be described using either of these formulas, as we will see in the examples that follow. A little bit more about on sequence notation. So we often denote sequences using letter A and indices as subscripts, so A1, A2, A3, and so on. First element is typically A1, nth element is AN. We also have this special notation for sums that we will use a lot in this course, using this Greek letter sigma. And so this formula here denotes the sum that goes from A1 all the way to AN. So that's just the shorthand for this long sum on the right. So we'll see that a lot in the upcoming lectures. Okay, let's look at a couple of sample problems. So on the right, you can see 4 example sequences. And we want to give recursive and closed form expressions for all of these sequences. Okay, so let's look at the first one. So let's look at the following sequence and try to write its closed and recursive form. So first of all, I find that it helps to write indices of the sequence underneath the sequence numbers to assist us in figuring out these forms. Next, we have to spot the pattern in the sequence. So the sequence we have is 4, 9, 16, 25, 36. What will be the next number? So this is 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Next will be 7 squared, which is 49. Then 8 squared, which is 64. So the closed form is really obvious at this point. And we can write it as an is equal to n plus 1 squared. Now we should double check our solution. So when the index is 1, a of 1 is equal to 1 plus 1, 2 squared is 4. When the end is 2, a of 2 is equal to 2 plus 1 is 3, squared is 9. A of 3 is equal to 3 plus 1, 4, squared is 16. And so this seems to be the correct closed form. Now let's try to write down the recursive form. I find that it helps to write down a couple of the first unravels of recursive form to help us out to spot the pattern. So A2 is equal to A1 plus 5. A3 is equal to A2 plus 7. A4 is equal to A3 plus 9, and so on. You can already notice a pattern forming here. So we have on the right hand side, I'll write down recursive definition. A1, don't forget the initialization, is equal to 4. AN is equal to AN minus 1 plus, well, something that is changing in every iteration, which means that it might be a good idea to relate it to n. So a of 2 plus two n sorry, 2n plus 1. So this is our recursive definition. So let's check it. A of 1 is equal to 4. We have 4. That's great. A of 2 is equal to A of 1, 4, plus 2 times 2 plus 1, plus 5. So A of 2 is equal to 4 plus 5, which is 9. All good. A of 3 is equal to A of 2, which is 9, plus 2 times 3, 6 plus 1 is 7. 9 plus 7, 16. Great. So this is indeed generating the sequence we wanted. And so now we have both the closed form, which is this, as well as recursive form, which is both of these because we have to initialize it for this number sequence. Wonderful. So let's do more of these examples. Let's do the following one. So here is another number sequence, and we want to find the closed and recursive form of this sequence. So as before, I will write indices underneath to assist me in figuring out the pattern in these forms. Now I will try to see what the pattern is. So we have 2, 4, 8, 16, 32, 64. So the next number should be 2 times the previous one. So we should have 128 here. And this is index 7. Yeah, so clearly this time maybe the recursive sequence is more obvious. So let's write down the recursive sequence first. We have to initialize it. Don't forget about it. A1 is equal to 2. And now we have to express the nth element of the sequence using the previous elements. So an is equal to 2 times a n minus 1. So this is our recursive form for this sequence. Now let's think about the closed form. If you look at the sequence, clearly there's some kind of power of 2 happening here. So at index 1 we have 2. That's 2 to the power of 1. At index 2 we have 4, 2 to the power of 2. And index 3 we have 8, 2 to the power of 3. So the closed form is an is equal to 2 to the power of n. So this sequence was a little bit easier than the previous one, I would say. This is our recursive form, and this is our closed form of the sequence. Don't forget, for the recursive form, we always need to look for the initialization part. And certainly in quizzes and homeworks, we'll make sure that you guys do not miss that. Okay. So what is important to notice here is that you do have to kind of figure out and mine these patterns from sequences. And as you do more and more of them, you will just spot them faster. And so I strongly suggest that you practice quite a few of them to be able to spot these patterns quickly. Okay, so we have another sequence. Let me maybe get this one started for you and you can finish it at home. You can pause the video and try to finish it on your own. So as before, let's mark our indices to help us out. We have 1, 5, 9, 13, 17. 5 is 4 plus 1, 9 is 4 plus 5, 13 is 4 plus 9, 17 is 4 plus 13. So the next one would be 17 plus 4, 21, and so on. So let's do the recursive form. and you guys can do the closed form. So A1 is equal to 1. Don't forget to initialize. And we already spotted the pattern basically. AN is equal to 4 plus AN minus 1. That's it. And you should attempt the closed form at home. Okay, let's do another one. Okay, let's do the sequence that starts with 1. So here we have to first write down the sequence on our own. So it starts with 1. And each entry is 6 more than the previous entry. So the next entry is going to be 7. 7 plus 6 is 13. Plus 6 is 19. Plus 6 is 25. And so on. Write down indices to help us out. The recursive forms is already giving us with this sentence. So A1 is equal to 1. And each entry, AN, is 6 plus the previous entry. So the problem basically already gave us the recursive form. That's how it was expressed. Let me stress out once more. This whole thing is recursive form. You need both the initial condition and the nth element expressed as the previous one. Okay, so what is the closed form? Let's think a little bit about that. Well, we see that we are adding 6 to the previous element, so it's probably some kind of multiplication of the index with 6. So let's try to write it down. AN is equal to 6 times n minus 1 plus 1. So let's check this. So when n is 1, we have 6 times 0 is 0 plus 1 is 1. When n is 2, we have 6 times 1 is 6 plus 1 is 7. When n is 3, 6 times 2, 12 plus 1 is 13. When n is 4, 6 times 3 is 18 plus 1 is 19 and so on. So we checked it, and this is indeed the closed form of this sequence. Okay, great. So hopefully you now understand and have a basic understanding for how to figure out closed and recursive form for sequences. In the rest of the lecture, I have 2 more examples, and I will leave this for you to solve at home. So I strongly encourage you, you can pause the video now and think about the sequence and try to follow the steps that I did and try to figure out the closed and recursive form of this sequence. And the same goes for this one. And we will revisit this on Tuesday briefly during our recitation. Finally, I just want to remind you about to-dos and know that these are also available on Canvas, and so you can find them there as well. And don't forget about them. Thank you all, and I'm really looking forward to seeing you all on Tuesday in our Zoom meeting. Bye.